Hello, my name is Mark Case, and today we're going to be taking a look at an experiment using electrolysis to cause a chemical change in a solution that contains both acetic acid and a little bit of sodium sulfate. What we're going to do is monitor the amount of energy that's being transferred, and this is going to be by measuring what are called coulombs. A coulomb is related to an amp of current that is transferred in 1 second. This relationship is part of the AP chemistry exam. You will find these formulas and also the definitions of a coulomb and an amp and other values such as a Faraday. And these are going to be utilized in terms of our experiment for today. What we're going to do is we're going to be utilizing a power source to be able to drive a reaction that's going to end up converting a little bit of the acid, the acetic acid that's going to be in the beaker, into hydrogen gas. So we want to be able to collect that using either a eudiometer, which is a gas collecting tube that's sealed on one end, or we could use a burette, or you could even use a graduated cylinder or a test tube, whatever you might have to be able to do that. You need to have some kind of ammeter that would be able to measure up to a maximum of 3 amps that you'd be working with. Your physics teacher might have some of those if you don't have any available, or you can go to a place like Harbor Freight and they sell a multimeter that will include an ammeter for about $9. It's the red one. And usually they have some giveaways where they might work with, you be able to get one for free. You could use something like a 9-volt battery to drive this reaction, but a 9-volt battery is basically consisting of 6 1.5 volts that are connected together, positive to negative throughout in what is called series. So even though it produces 9 volts, it's going to be lucky if you can get about 0.1 or 0.15 amps energy out of it. So it's not very powerful for driving the reaction. Not only that, it will eventually probably wear down your battery, that if you collect 50 milliliters, you're going to drain about 50% of the battery strength. You could also do a lantern battery, a 6-volt, but those are relatively expensive. But the idea there is that the batteries are not only connected of plus minus in terms of putting them and linking them so that they're in series, but they're also in parallel. And what that means is that you have multiple cells that have the positives connected to each other, multiple cells that have the negatives connected to each other. So when you do that in parallel, you increase the amperage, but the voltage remains basically the same. We're going to be using a power source today because that's even better, because you have an external AC current that's passing through it, and that'll convert it into DC volts going into your setup, and it also can measure the ammeter as well. Let me pause for a moment here and be able to show you the actual setup that we're going to be using, and then we'll go from there. We have this set up now so that the eudiometer has been filled with the same solution, the acetic acid sodium sulfate mix, and you put the end of a copper wire that's insulated except at the very tips into that eudiometer and flip it over. Now, it's tough to get a good seal when you do this, so normally what will happen is that you'll have a little bit of a air bubble that'll form on top. And what you have to do is just assume that that's your starting point and see how much additional amount of gas you have added to it. Now, as far as the connection goes, this is hooked up to the black wire that goes over to our copper and fastens onto that one. So the copper wire from the power source is the negative terminal. That means electrons are flowing into the copper from the power source. The zinc, on the other hand, is connected to the red wire, and that's the one that is connected to the positive terminal associated with your power source. Normally, what would happen if we just put the zinc into this solution, the copper is not doing any bubbling, as you may see, but if I would just quickly put the zinc down inside, it's going to start reacting because it's in an acid, and you're going to start getting some bubbling that's going to occur on the outside of the eudiometer. So that would end up being some of the gas being lost in this particular reaction. I'm going to set that down inside here. And what I'm going to do is I'm going to turn on the power. Let's try to set this way so you can. Come on. Not cooperating today, so it may be blocking your view, but I apologize for that. We're going to turn up the voltage. And what we're going to try to do is to set the voltage first so that we end up with about 12 volts. So that's on the left-hand side. Now you'll notice you're getting some bubbles that are starting to form inside of the eudiometer. If you were using a, let's hit the start button here. If you were using a 9-volt battery, you might only be getting, 0.25 amps. But what we have the ability to do is we can adjust the current and we can increase the amperage which will speed up the reaction that's going to be taking place. What you want to do is you want to monitor what the amount of amperage is that you're able to produce. And we might be able to tweak this a little bit higher. Trying to get this set within the first minute or so. And I'm going to stop at that point. So I have 32 volts. I'm really have it cranked up at that first minute, but that now is generating the gas at a much faster rate than if we were doing this with the 9-volt battery. We would be sitting here for about a half an hour to get maybe 25 milliliters with the 9-volt. And in this case, it's going to react much more rapidly. So what I'm going to do is I'm going to allow the timer to keep running. I'm going to monitor what the amps are and try to keep them fairly consistent once it levels off. So it looks like right now it's about 0.77, 0.76. It was bouncing a little bit. When we hit our second minute on the timer, what we want to do is we want to have an idea what was the approximate average of the amps that we ran that for. So we have to keep track of the amps that were running through and the number of seconds that it was running for. Looks like it's stabilized at 0.78. So now we're running it for the third minute. And we're just going to let this keep running. You're watching bubbles form in that reaction. And we're going to let this go for a little bit. And if it gets up above 0.78, I'm at 0.80. I'm going to try to freeze it at that point. I will adjust the voltage a little bit, change the current a little bit, try to keep that fairly consistent right around that value for the next couple minutes that we're running this for. So I'm going to pause the video here and we'll come back in a little bit and see where we're at. So we've just hit our 5-minute mark. And right now we're looking at about 25 milliliters of the hydrogen gas that has been collected. If you recall from any gas experiments that you're working with in a aqueous environment, there's not only water, not only hydrogen, but there's also some water vapor that's trapped inside there. So we're going to need to do a temperature check and find out what is the temperature of this mixture as it's progressing, because that will affect the amount of vapor pressure created by water from the water displacement process involved here. So I'm going to pause the recording of this, but I'm going to let the experiment keep running. I'm still maintaining at about a 0.80 for the last couple minutes that we have, and we'll come back, check on it in a little bit. We are just hitting the 10-minute mark, and at this point, we're still holding at about 0.8 as our average amp reading. And every time it goes a little higher, I tweak the voltage back a little bit. Anytime it goes a little lower, I raise it up a little bit. Our volume at this point, looking at the cylinder, is basically where we're at. About 62 milliliters have been collected. So I could stop at any time at this stage. The eudiometer that I'm using is a 100 milliliter eudiometer, which is much bigger than I normally work with, but this is what I had available to use. So I'm going to let it go a little further, because what we have to do here is we have to equalize the water level that's inside of the eudiometer and also that's in the beaker. If you don't equalize those two, that means that the pressure of the trapped gases in the eudiometer, which is the hydrogen, and then also you have your water vapor, if you don't equalize that, then it doesn't equal the atmospheric pressure. Now, we used to have a mercury barometer in the lab, but that's been removed. So to get your atmospheric pressure, what you can do is just check your local weather station, and they'll be able to tell you what the atmospheric pressure is for that day. It's not going to be perfect, but it's something that you could use for your measurement itself. And I'm getting down to a stage where I'm now passing a collected volume roughly at about 70 milliliters that I've absorbed. So I'm going to wait till I get to the last minute reading here. And I wasn't paying attention. My amps bumped up a little bit. So that sort of balances out when I was a little bit lower than 0.8. Again, you want to be fairly accurate on your reading and average that you get over that time. So I'm at 12 minutes. We'll let it go to lucky 13 because that's the perfect place to stop. And then we'll do our final measurements and the changes that will occur. So I'll see you back in 40 seconds. So we just paused right at 13 minutes and turned off the power. What you also have to do at that point is you have to take the zinc out of the solution. Otherwise, it'll start reacting together with any of the leftover hydrogen ions that are present in there from our mixture that we were working with. The height of this, to be able to read that a little bit more accurately, what I do is I just take and put a black or dark piece of paper behind that, and then I can see where that water level is and get a very accurate reading for that value. So right now it's a little bit past 90. You'd have to look straight on at it so that you don't get a parallax error and you're looking at the bottom of the meniscus. So it's a little over 90, and I started out originally at about 8.8 milliliters for the initial volume reading. Before I take my final reading on here, what I'm going to do is I'm going to allow it to stabilize and have any bubbles that are still floating up to eventually level off. And then we're also going to try to measure the two height differences. So I'm going to pause my recording at this point and come back in a few minutes. Okay, so I waited about 5 minutes to allow the temperature to stabilize. I have a thermometer that's down inside there. It's easier if I use the white background here to help to be able to see that. And in this case, what we're looking at is this at about 32 degrees. So the red mark up there is just above the 31, so say 32 degrees for that setup. Excuse me. For looking at our volume reading, if I put this behind here and take an estimate of what that is, each one of the marks that are on here represents 0.2 milliliters. So this looks like it's about 90, no, I take that back, about 89.4 as our reading that we have there, 89.4 as the final volume. And then the last thing we have to measure is what's the difference in the height, because we don't have them equalized. So if I put a ruler down inside here and get it so that it's just sitting, you got to use the inch side, not the centimeter side, because we're talking about inches of mercury. We could do a metric conversion, but let's not go crazy here. So we set it so that it starts at the 0 point, and then we look where it will be when it's the level of the water that we have. And the level of the water looks like it's right at about 3¼ So when I have this just sitting into the water level below, it's at about 3¼ or 3.25 inches. That's the difference in the water height. And we have to make an adjustment for that. For every inch of mercury, you need 13.6 inches of water. So that would allow you to convert this from a water level into a mercury level. You can take a look at inches and convert those into millimeters or centimeters. Basically, atmospheric pressure, the standard pressure is 760 millimeters of mercury. So how many inches would that be equivalent to? Well, there's 2.54 centimeters per inch. You do the math. Chemistry is math, math is chemistry. So you now have the basic information that you need. You know that it ran for a total of 13 minutes. The average amp reading was 0.80. And now what's left for you is to do the calculations, be able to try to figure out what would be the amount of coulombs of energy that was transferred. You may recall that an electron has a charge on it based on a single electron. And this charge value is 1.602 times 10 to the negative 19th coulombs. You also know Avogadro's number. Basically, you're saying that Avogadro's number is 6.02 times 10 to the 23rd particles, whatever those might be, per mole that you have. In this case, we're trying to correlate the coulombs to the particles or the moles that you have for your setup. So do your calculations, determine what your values are. I have one final data thing that I have to take care of, because we not only can look at the change that occurred relative to the hydrogen that was generated in our process, but we could also do it based on the amount of zinc that was lost as far as a mass goes, and see if that can be used to also calculate the same information about looking at what is a Faraday, and also what would be the equivalent of Avogadro's number for a mole for that particular setup. So we'll see you as you work through your calculations. Your teacher will give you some assistance, and good luck. Have a nice day. And these are the initial mass values and final mass value after the electrolysis of the zinc that was used. You notice that in the first trial, it was very shiny, it was cleaned up, there was no corrosion on it. And then after the electrolysis, there's a lot of residue, a lot of products that have formed on the process of that from some kind of interaction going on with the solution directly. So that's also could be used to figure out Faraday's constant and be able to calculate what would be the value of Avogadro's number. But keep in mind that some of the reaction is going to occur directly with the solution and not be accounted for in terms of looking at the electrolysis process that's driving this reaction. So good luck on your calculations. Your teacher can offer you some assistance, and have a great day.